You guys see my screen?
Yes.
Yes.
Yeah. So basically, topic will be loss and loss functions for training a deep neural networks. Now, our roadmap will be first we'll be watching how neural network learning as optimization. Learning happens as optimization. Then, what is loss function and loss? Then there will be a framework. There is a framework which is being used, that is maximum likelihood. Then we'll check what is maximum likelihood and cross entropy. Then what loss function to be used. After that, I'll show some pseudocodes of how to implement the loss function, and then at the end we'll see how loss function and how it affects or it reports the model performance. So this is the agenda today, and it will be quick and theoretical session. So yeah. Then first of all, what like neural network learning as optimization. So how basically a neural network works. So what a deep learning neural network learns is it maps a set of inputs to a set of outputs from a training data. Now we cannot calculate like what happens is there will be let's say a black box is here. There will be some certain inputs coming in, and there will be some output there. Output in the sense, if I am passing 5 or 10 as an input and I am getting 15 as an output, that means that black box is addition of those two inputs. There will be many parameters aligning to it. So I know the output, I know the input, I want to adjust my black box in order to achieve the output, provided what is the input. So it's about a single black box. Now this black box will have uh, so many nodes, like so many components inside it, that will have some specific parameters, weights that has to be adjusted in order to get the output. Now we can and as it's a black box, we cannot, and it has so many nodes, we cannot calculate perfect weights for complete neural network, as it has too many unknowns. So instead what we do its learning is like a cast as a search or optimization of a problem. Now what happens is there will be an algorithm which will be used to navigate the space, like navigate, let's say I have a set of possible weights. For example, the basic example is 5 plus 10 gives me 15. So there are set of operations which are possible, like addition, subtraction, multiplication. So there will be possible set of weights a model can use in order to make a prediction or a good enough prediction. So what a learning system does is it searches for all the possible set of weights a model can have, and then find out the optimum weight which can be used to give a good prediction. Now, typically, what a neural network model is trained using stochastic gradient descent. Now, what the stochastic means? Now, in day-to-day life, we use like I think this is 50% probable to be a cat. Or if I see a cat or a dog, I see like I have something in my mind saying that this can be dog or this can be cat, but I think it is 90% dog and 10% cat. So wherever I do a prediction or I recognize something, there exists a probability. No, now what a network does is stochastic means something that has a probability distribution. Now I will what how training happens is the system tries to decrease the errors in the sense, like I have a cat and a dog. I am predicting something to be dog, but in the training set that is a cat. So there is an error that it is a cat, but I am predicting it a dog. So there will be an error between those. So difference between the error I am trying to minimize. So am I clear on that? Hello? Hello? Am I audible?
Yeah, yeah.
Yes.
Yeah.
Yeah.
So what I am trying to do here is there will be some actual probability distribution, like this person or a animal is a cat or a dog, and there will be some predictions happening on the other side. So I will find difference between those two things, and I will get a error out of it. Like this should be the actual thing. This is what I am getting, and difference between them is the error. So I will try to minimize this error and update my weights in such a way that I get a optimum thing. So every time minimizing, like let's say I'm getting a error as like I'm getting 2% error, but sometimes it might happen that my system is giving optimum performance not at 2% error but at 5% error. So always it is not necessary that minimum the error is optimum is my system is. So this kind of optimization algorithm is known as stochastic gradient descent optimization algorithm, and weights are updated instead using back propagation of error rate algorithm. Now, what the term back propagation means? Back propagation is basically, in a layman term, what I would say is, I have some set of inputs, I have an output, I will set all the parameters randomly. Now I will check what I am getting as output. Now I will match the difference between what output I should get and what output I am getting. Now the difference between them, let's say it's 5%. Then I will adjust all my parameters again in order to reduce that error or optimize that error. Then at the end of the propagation, I'll get some optimum value. So since I am at the output side and I am back propagating in changing parameters towards the input, so that is basically known as back propagation. Now, the gradient in descent refers to the error gradient. Gradient is normal terms we say is gradients means difference between something. So here gradient means refers to the error gradient. Now the model with a given set of weights is used to make prediction, and error for those predictions is calculated. Now the gradient descent algorithm seeks to change the weights so that next evaluation reduces the error, and meaning that optimization algorithm navigating down the gradient or the slope of error. Now we basically what we do is we have some like we plot it over a graph saying I'm getting this error. Now I will try to reduce that error, or I will that gradient or the slope of that error graph tries to come down. So this is basically a representation where I can visualize gradient descent. So now that we know that training neural networks solves an optimization problem, we can look at how the error of the given set of weights is calculated. Now, we know now we know that what is basically how the neural network is trained. Then how what is the algorithm being used in giving the optimum solution? Now, like it's an optimization problem. So now we can see what is a loss function and the loss. So in context of optimization algorithm, the function used to evaluate the candidate solution that is a set of weights, is represented as an objective function. Now what happens is, as I said, there will be a black box between the input and the output. Now the set of weights which are used to evaluate the candidate solution, that is known as objective function. So we may seek to maximize or minimize that objective function. That meaning that we are searching for a solution that has highest or the lowest score respectively. Now, what does this highest or the lowest score means? When I talk on the lowest score side, basically I'm talking about the errors. So we are seeking to minimize the errors. Such, the objective function is often referred to as cost function or a loss function, and the value calculated by the loss function is known as loss. Now there is something called objective function. That objective function we are seeking to maximize or minimize. In the case we are seeking for that objective function to minimize the error, so that value calculated by the function is referred to as loss. Now the cost or the loss function has an important job in that it must faithfully distill all aspects of the model down to a single number, and such a way that improvements in the number are sign of a better model. Now, as I said earlier, it's not always I am getting 2% error, that means my model is better. So it should faithfully satisfy all the aspects of the model to get a single number in order to get my predictions better. So if I'm getting a 2% error, but I am classifying a cat as a dog, that means my model is in fact better. But if I am getting even 5% error and still my model is able to detect or the classify things perfectly, then it's a better model. So this is what is loss function or a loss. Then there is a framework. So there are many functions that could be used to estimate the error of set of weights in a neural network. Now we prefer a function where the space of we are preferring a function where all the solution can be mapped to a smooth landscape, that this optimization algorithm can reasonably navigate through all the possible solutions, and iteratively it can update the weight. So what is maximum likelihood estimation? Now it's a framework for the inference for finding the best statistical estimates of the parameters from the historical training data. Now, what is this? It is basically a framework. So it infers and for finding the best estimate of those parameters in the black box, considering what was my historical or what was my training data. So, which is what we are trying to do with the neural network. Like we are trying to adjust all our parameters based on the training data which we provide to get the best optimal solution. Now we have a training data set with one or more input variables. We require a model to estimate the weight of the parameters that best maps the example of inputs to the target output. Now, given input, a model is trying to make the prediction that matches the data distribution of the target variable. Under maximum likelihood, a loss function estimates how closely the distribution of the prediction made by the model matches the distribution of the target variables in the training data. Now, as I said, there is some distribution of the prediction probabilities there will be some probability distribution in prediction, and there will be some prediction, some distribution of the probability in the training data. Now, how different, like what is the difference between both these distribution is the estimate which is given by the loss function. So basically, what I tend to minimize the losses. That is what I am getting actually and what I should get actually. So yeah, and the benefit of using this maximum likelihood as a framework for estimating parameters is that the number of examples in the training data set is increased. As we increase the training examples, the estimates of the model parameters improves. And this is called the property of consistency. Yeah. So now talking about are things clear till here?
Yeah.
Yeah. So,
Yes.
so next we'll talk about what is maximum likelihood and cross entropy. Now, under this framework, the error between two distribution is measured using cross entropy. So we are cross entropy basically is um, what we say a measure or like it's I can give the clear definition after we do this maybe. Yeah. So it's something we are using to calculate the probability the error between the two probability distribution. That's what I can say. So then when modeling a classification problem, we are interested to map a class label. So for example, what happens is I have just two classes. That is a binary classification problem. There are some classes. Let's say there cat is a class, dog is a class. I have an image. I want to classify that particular image to either cat or dog. So both will have some probability. Like this image has a probability, that probability is between 0 or 1. Either this image can belong to class cat or it can belong to class dog. So that is a binary classification problem where I want to classify my object uh, to a particular class within two classes, and there will be a probability, like there will be classification problem where I have multiple classes as in this particular image might belong, like basically more than two classes. It might belong to a class person, cat, dog, raccoon, and so on. So that is known as multiple classification class classification problem. So I will have to find out the probability of a picture belonging to each of the class. So these are basically classification problems which we are trying to address. So in a training data set, the probability of example belonging to a class would be 0 or 1 in the binary classification problem, and each will have and in multiple class classification problem it will have a probability related to each of the class which exist in the space. Now, therefore, under maximum likelihood estimation, we would seek a set of model weights that minimize the difference between models' predicted probability distribution given dataset and the distribution of the probability in the training dataset, which is called cross entropy. So basically, cross entropy is nothing but it is used to find the difference between the model's predicted probability distribution and the distribution of probability in the training dataset. So this is the classification problem. Now another problem is called regression problem. So what the regression problem is, like in classification problem, I am deciding an entity. I am classifying the entity to belonging to some class. Let's say, for example, an entity can belong to cat class or entity can belong to dog class. So that is a classification problem. Now, when I talk about regression problem, it will have some quantity, like some quantity has to be predicted. For example, weight or salary or so, like that. So some, instead of classifying, there will be some quantity number that will be predicted. So that is known as the regression problem. So in classification problem, we use cross entropy, and in regression problem, mean squared error loss function is used instead commonly. So next, most of the modern neural networks are trained using maximum likelihood. This means that the cost function is described as cross entropy between the training data and the model's distribution. Now, the maximum likelihood approach was adopted most universally, not just because of the theoretical framework, but primarily because of results it produced. Now, specifically neural networks for classification that uses a sigmoid or softmax activation function in the output layer. So, what is sigmoid function? What is a softmax function? What is a logarithmic function? What is linear regression? So these are some activation functions which like sigmoid function is like something when we plot on graph, takes a curve like S shape curve. For example, log curves are S shape curves, but sigmoid function is mostly for binary cross entropy, whereas softmax activation function is for multi-dimensional space, as in I have multiple thing. And what happens is, specifically where my model performance depends is what is my activation function in the output layer and what type of loss function I am using. So specifically, neural networks for classification problem that uses sigmoid or softmax function in the output layer learns faster and more robustly using a cross entropy or loss function. So this is here what we see, that it is very important to choose a combination of activation function and the loss function in the output layer in order to get better performance. Yeah. So next is what loss function to be used. So we can summarize from previous section that directly suggests that loss function that you should use under a framework of maximum likelihood. Importantly, the choice of loss function is directly related to the activation function used in the output layer of the neural network. So these two elements are interconnected. So what is interconnected is activation function at the output layer and the loss function which we are using. So think of the configuration at the output layer as a choice of framing your prediction problem, and the choice of loss function as the way to calculate the error for given framing, giving framing your problem. So now what we'll do, we'll review basically three types of problems, and what are best practices or default values for each problem with regard to output layer and loss functions. So here I have taken three types of problems, like one is the regression problem, one is binary classification, and the third one is multi-class classification. So what the regression problem is, a problem where you are predicting some real value quantity. For example, I'm predicting of weight of something, I'm predicting some salary, I'm predicting something else that has some quantitative value. In binary classification, there will be two classes. I have to categorize my entity into either of the one class. Then multi-class classification, when I have more than two classes. So in regression problem, what will be there? There is some like configuration based on output layer configuration and the loss function, their relation, which are used by default, or what are followed as the best practices. So if my output layer config, like if it is a regression problem and my output layer configuration used is one node with linear activation unit, I am tend to use loss function mean squared error as a loss function. Now, what is mean squared error? So these are basically we'll see in next slide like how these are implemented. So I have two types of error function here. There will be mean squared error and there will be cross entropy. So based on problem, I will be using those. So in binary classification, what happens is when I have binary classification, I will use one node with sigmoid activation unit in the output layer, and loss function will be cross entropy, that is also referred to as logarithmic loss. Now here, so what happens is cross entropy is like we can say we have a space and subspaces. So yeah, so sigmoid function is used where I have just two classes, and softmax function will be used when I have a multidimensional probability distribution. So in multi-class classification, output layer configuration will be like one node with for each class using a softmax activation function, and loss function will be cross entropy, which is also referred to as logarithmic loss. This is the default or best practices for each of the problem types with regard to output layer and loss function. Now we'll see how the implementation works for these loss functions. So first of all, if I talk about the mean square error, so what it does is it is calculated as the average of square difference between the predicted and actual values. So what if you see in the below code snippet, I have a mean squared error function. It has inputs called actual and predicted. So what it does is it will take difference between those actual and predicted, do a square of it, add all values, all probability values, and then like divide it by length of actual, like take a mean of that square error. That is, and that is known as mean squared error. So it will take all the actual probability values, like subtracted from all the predicted probability values, then do a square of it and adds all such of these, like actual I minus predicted I, square of it, and add to actual j minus predicted j and square of it. Then when once I get all the sum, I will divide by how many actual values were there. So that is basically known as mean squared error. So the result will be always positive regardless of the sign of the predicted and actual values. And the perfect value is 0. So the loss value is minimized, although it can be used in maximization optimization process by making the score negative. Now the code snippet is showing like a pseudocode. It's a pseudocode for the implementation of mean squared error. So here is a note like what all implementation I am showing here are ideal states when all like sum of all the probabilities adds up to 1. So in multi-class classification, sometimes it happens that all the probability of belonging of a object belonging to each class doesn't adds up to 1. So in that case, this doesn't work. Okay. So cross entropy loss. So it's simply referred to as a cross entropy, logarithmic loss, logistic loss, or a log loss for short. So these are different names to it. Now each predicted probability is compared to the actual class probability value, 0 or 1, and the score is calculated that panelize the probability based on distance from the expected value. Now, distance from the expected value is if we are plotting these values on the graph. So I am getting value somewhere, and I should actually get value somewhere else. So distance between that is the error which I am getting, and the penalty is logarithmic, offering a small score that differences from like 0.1 or 0.2. So, or and enormous score for a large difference like 0.9 or 1.0. So cross entropy loss is minimized, where smaller values represent better models than larger values. So a model that predicts perfect probability has a cross entropy loss or the log loss of 0.0. So cross entropy for a binary or the two class prediction problem is calculated as average cross entropy across all examples. So this is the code snippet here. So here if you see the difference here is we are using logarithmic and we are adding some 1 to the power minus like e to the power minus 50. So we are adding the small value to the predicted value so that like even in case my this value shouldn't be equals to 0. So if it becomes 0, yeah, so that the I want to avoid here calculating the log of 0. That's why I'm adding exponential to the power 50. So this means that the best practice, the best possible loss will be ever calculated will have value closer to 0 but not 0. Yeah. So this is for binary cross entropy where I have just two classes and I will simply put a log outside the predicted value. So if I have multiple class classification problem, so what I will do is I will have probability related to each class. As I said earlier, it only works in case if all probability distributions adds up to 1. So here if you see for this is pseudo code, here one more loop came inside this. So I have actual I have actual j, and then I have predicted of I and j. So each like a particular entity will have a probability related to each class in a multi-class classification problem. Then the mean sum score formula will be the same. Yeah. So now loss function and the reported model performance. So nevertheless, we may or may not want to report performance of the model using loss function. But for example, logarithmic loss is challenging to interpret, especially for a like non-machine learning practitioner. It is challenging to interpret. The same can be said for mean squared error. Now, instead, it may be more important to report the accuracy and root mean square error for the models used for classification and regression respectively. So it may also be desirable to choose models based on metrics instead of loss. So this is an important consideration as the model with minimum loss may or may not be the model with best metric that is important to the project stakeholders. So it always depends on what is my problem statement, what activation function I want to use, what I want to see as the output, is it the error or the accuracy, and what my best metric that my stakeholder wants to see. So yeah. So what I expect you what this was all about is neural networks are trained using an optimization process that requires the loss function to calculate the model error. Now, maximum likelihood provides a framework for choosing a loss function when training neural network and machine learning models in general. And the third one is cross entropy and mean square error are the two main types of loss function to use when training a neural network model. So these are the three key takeaways I expect. This should be grabbed out of it. Yeah. Any questions?
Oh, I have one question.
Mm-hmm.
There are classes in binary classification and multiple classification, right? So,
Mm-hmm.
how from get these classes?
Uh-huh.
there are classes in binary classification and multiple classification, no? So
Mhm.
from where do you get these classes or determine like what classes to be used?
So these things are provided in, like, while doing training. I will define that I have these many classes. Let's say I have 5 classes. I will initially define that yes, I have 5 classes, and I will tell my network. I will mention my network that you will have to classify these like whatever inputs come to you in these 5 predefined classes. So if it is like classes are defined by the user itself,
Okay.
predefined.
Hmm.
Anything else?
How are the like weights and biases used? Like are what's the difference between them in the
So
equation?
when we talk about a single, this black hole box will have so many neurons in the, or we say, I can say components. So many components will be there. So there will be one function. So why we say a function as an activation function is until unless I get to the activation threshold, it won't fire the output. So there are certain weights connected to it. So weights are basically multiplied to the input, and biases are some addition or subtraction to the output I am getting after the weights. So all this together is fed to activation function, and after a certain threshold, it fires up the output. I think I'm clear.
So basically, the weights, like it's the weights and biases are always different for every sort of input, right?
uh, Always, yeah. So here what we are trying to achieve, yeah, is like I have a complete layer which have some n number of inputs. Every input or every component will have its own weight and bias. Let's say my input keeps on changing, so what my end goal is, this weight and bias should be settled that the end output is optimum, means I am getting minimum error out of it. Like I may not be 100% or 90% sure, but somewhere I am 80% sure setting this weight and bias value.
So basically, the predicted output should be close to the, like as much as possible, close to the actual output.
Yes, so it follows back propagation. Like it has some input, it will have an output. Now there will be some randomly set weights and biases. Once it will like go from input till output, then it checks whether I have achieved the actual thing. No, then it will back propagate and reset, like keep setting all the weights and biases. So it's when we see single perceptron problem and then replicate it. Let's say I have n number of neurons. So same thing happens for all.
Okay.
Or coach.
Mm, no, I think that's it.
Okay. थैंक यू. दीप्ति कुछ समझ में आया क्या?
हाँ हाँ.
ओके, थैंक यू.
Thank you.
चलो, thank you
Thank
for all for joining, and I have uploaded this to AI sessions file.
Thank you.
Okay.
Bye bye.
Oh,
Cool.
okay.
Thank you.
Yeah. Thank you.
Bye.